So what we're going to be doing today, we're going to talk about another storage element, which is inductors, right? So last time we talked about like capacitors, and we said like capacitors store energy in an electric field. And we said there is like another type of like storage element, which is stores energy in a magnetic field. And we call that inductors. Let me quickly review whatever we had for capacitors, and then move on to the inductors. So let's say I have a capacitor. So this is review. Capacitors are storage elements that store energy in an electric field. And we said if we have like two plates, two conductors, separated by a dielectric, the charges on those two plates are proportional to the potential difference, which created an electric field, right? And we said the constant that makes the proportionality an equality was called a capacitance. So we have Q equals CV. And given this, we said if we have a circuit that's connected to a capacitor, if current through the capacitor is I of t, voltage across the capacitor is V of t, and the value of the capacitor is C, current through capacitor is C dVt dt. So the relationship between I and V is through a derivative. And we said, since we know derivative is a linear operator, we can find the inverse of it and find the relationship between V and I, which we wrote V of t as integral from minus infinity to t, 1 over c I tau d tau. Right? We also talked about if we wanted our initial condition not to be negative infinity, right? We just needed to like break down like the integral to like two integrals and write that portion in terms of the initial condition I, right? We said if we have voltage across a capacitor, since voltage across a capacitor is written in terms of integral, it is a continuous function. So voltage across a capacitor is a continuous function, which what it meant was if I have like some voltage T, which is voltage across the capacitor, if I look at the voltage at any given time t, and if I look at the value of Vt a little bit before that given time t, and a little bit after that time t, these two values should be the same. So if I call this Vt negative, call this Vt positive, I know Vt negative must be the same as Vt positive. What it basically means is that there is no jump in the voltage, which we could not say the same about the current because current was the derivative, right? And it's not necessarily a continuous function. So we might have discontinuity, right? Another thing we talked about was the energy stored in a capacitor. We said this energy is half the value of the capacitor times voltage across the capacitor squared, right? We also talked about the connections. We said if we have a bunch of like capacitors in series, let's just call them C1, C2, all the way to Cn, I can replace this by one capacitor, and the value of the capacitor for the series resembled a bunch of like resistors in parallel. So if I want to replace this by C equivalent, in this case, C equivalent can be computed using this formula. Right? And if we have them in parallel, C1, C2, all the way to Cn, I can replace this by one capacitor. And this time, equivalent is C1 plus C2 all the way to C. Right? And we did like an example as to like how we can compute these things. Right? But before we moving on to inductors, let's talk about like capacitors and how they work in a circuit intuitively. Right? We're going to get to like the equations on like how they work like mathematically, but let's just think about it for a second in terms of like intuition. Okay? Let's just say I'm given a circuit, so intuition. Let's just say I'm given a circuit. I have some source Vs. It's connected to some resistor. And then I have a switch. And I have that connected to a capacitor with value C. And let's just say voltage across it is Vc of t. Right? At time t equals t naught, I change the position of the switch to here and connect the capacitor to a resistor like this. So at t equals t naught, switch changes position. Right? Let's see like what happens. So before t equals t naught, the switch is in this position. Right? So what it means is that if I have like a capacitor, since I have a source in there, this source Vs starts supplying the entire circuit that I have, right? And my capacitor starts having voltage across it, which means this capacitor is being charged, right? And this keeps happening till time t equals t naught, which I immediately change position, and I go to this side, right? So at t equals t naught, this is the position that I have, right? So what it means is that I disconnect the capacitor from this side of the circuit. Now, if I look at this portion of the circuit, there is no source to supply the circuit. However, since my capacitor was already charged, so it means there is some voltage across it. So this capacitor, it starts acting like a supply source, and it starts supplying the entire circuit till it's completely discharged. Right? So if I want to just draw how it works, so let's just say this is voltage across capacitor, and this is time. So what's happening is that I'm going to have this capacitor charged up to time t naught. Let's just say this is time t naught. So the capacitor is being charged. This is a charging time. But as soon as I hit this t naught, since I no longer have any source to supply the circuit, this capacitor starts supplying till it becomes completely discharged. So it becomes discharged like this. So this is discharged. Right? how we get like these graphs and why they look like exponential and all those things, we're going to talk about it in detail. But what's important here is that for this portion from 0 to t naught, I have a source that can supply the circuit, which starts charging my capacitor. So I'm going to start seeing voltage across that capacitor. And as soon as I hit time t naught, the switch changes position, and the capacitor becomes a supplier. So it's just supplying the rest of the circuit, right? And it keeps happening till it's completely discharged, right? We're going to talk about like the equations for those, but like intuitively, this is what's happening, right? Does that make sense? Yes? So now we got this out of the way. Let's talk about inductors. Again, as we talked about it before, inductors are also storage elements, but they store energy in magnetic field. So inductors are storage elements that store energy in a magnetic field. Right? But let's see how it works. Let's just say we have a conductor, right? If we have a conductor, there is going to be some current flowing through it, right? If I have current flowing through a conductor, it automatically creates magnetic field. And the value of this magnetic field is proportional to the value of the current. So let's quickly write it down. Assume current flows through a conductor. This sets up a magnetic field. Let's just call that phi. Right? And we know the value of this phi is proportional to current I. Right? The rate that this phi, this magnetic field, changes over time gives us potential difference. Right? So the rate that magnetic field changes on a conductor creates potential difference. So we know V is proportional to the rate that this magnetic field is changing. But I know phi is proportional to the I. Therefore, d phi dt is proportional to di dt. Right? As always, when we're trying to make a proportionality an equality, we need to multiply it by constant. So to make proportionality an equality, we're going to multiply that proportionality by constant. We call this constant inductance. Right? And the unit for this inductance is Henry. Right? This is basically how we have like an inductor. So to summarize it, I have an inductor which we show it by this little thing. So let's just say this is my circuit. Let's just say current through this inductor is IT, value of it is L, voltage across it is VT. I know the relationship between V and I is L dit dt. And again, we know derivative is a linear operator, so we can find the inverse of it. And the inverse of this thing is indeed an integral. So I can find the relationship between I and V. So the relationship between I and V is IT equals negative infinity to t, 1 over L, V tau, d tau. Right? And of course, we have this plus I evaluated at negative infinity, which we know it is 0. Right? So what this tells me is that if my initial time is negative infinity, if I want to find current through the inductor at any given time t, it can be computed through that integral. If I change my initial condition to like some t naught rather than infinity, negative infinity, just like what we did for the capacitor, we can break down this integral and write it in terms of that initial value. So in general, I of t can be written as t naught to t, 1 over L v tau d tau plus I at t naught. Right? And again, this equation is exactly the same as the equation on the top. As soon as I change t naught to negative infinity, I at negative infinity is 0, and the integral is exactly the same as the integral at the top. Right? Remark? We were able to write I of t in terms of an integral. What it means is that current through an inductor is continuous. Since we wrote I of t in terms of an integral, it is a continuous function. Again, what it means is that if I look at current through inductor, is if this is the graph for it, if I look at any given time t, if I look at it a little bit before this t and a little bit after this t, and call it it negative and this it positive, it negative must be the same as it positive. What it means is that there's not going to be any jump in the current. Right? And as you can see, if I had a capacitor, voltage was continuous, which tells me if I write KVLs, I prefer to write KVLs for, if I have a circuit with like a capacitor, I prefer to write it in terms of voltages, so I can use the continuity of voltage to come up with the initial conditions. And if I do the same thing for an inductor, I prefer to write KCLs for I's to be able to use the continuity condition that we have. We're going to basically go through that in details later, but keep that in mind. If I have a circuit that has a capacitor in it, voltage across capacitor is always continuous. If I have a circuit with an inductor in it, current through inductor is always continuous. Right? And if you look at all these equations that we have over here, if I replace L by C, I by V, and V by I get like the other set of equations. And in this sense, capacitors and inductors are kind of dual of each other. Right? But let's table that for a second and go back to like whatever we have over here. If I have an inductor, current through the inductor must be continuous, right? What happens if current through an inductor is constant? So what happens if current through an inductor is constant? What do you think is happening? Well, if current through inductor is constant, it means the derivative of the current must be 0, right? If derivative of current is 0, what is voltage? It is 0. What does it mean to have voltage across an element 0? It means it looks like a short circuit, right? So what it means is that voltage must be 0, and therefore inductor looks like a short circuit, right? And as you recall, for capacitors and for like resistors, we had like some convention. If current hit the negative sign, the voltage was like negative, and so on and so forth. We have exact same thing over here as well. So let me quickly write down the conventions. Let's just say I have some IT that's going into my inductor, and this is VT. I know VT is L dit dt with the positive sign because I of t is hitting the positive sign. How about over here? I have L, this is VT, and current is going this way. How about this? Well, if you look at it, current is going from the negative side to the positive side. So it hits the negative first. So VT is negative L dit dt. Right? How about here? I have I of t. I have this is negative, this is positive. This is V of t. How about here? Is VT positive or negative? It's negative because we're hitting the negative sign first. So VT is negative L dit dt. And the same thing with this. If I have L, this is IT, this is negative, this is positive. How about VT over here? Is it positive or negative? It's positive because I is going from this side. So it hits the positive side first. So it's L dit. Right? Right? Any question on these things? Is that clear what we're doing? Yes? So just like what we did for capacitors, that we were able to like combine them and simplify them down to like one capacitor, or we were able to do the same for resistors, we're able to do the same thing for inductors as well. So let's talk about like connections. Connections. Again, we have two types of like connections. Series connections, which means I have a bunch of like inductors back to back. Let's just call this L1, L2, and Ln. And if I wanted to replace all these inductors back that are back to back with one, I can do that and call that value L equivalent. And it turns out L equivalent is L1 plus L2 plus Ln, which is similar to series resistors. Right? How do we find that L equivalent? It's exactly the same way that we found R equivalent, right? We know current through L1 is the same as current through L2, is the same as current through Ln. And if I look at voltage from A to B, in the first circuit, that should be the same as voltage from A to B in the second circuit, which is the equivalent circuit. In the first circuit, voltage between A and B is V across L1 plus V across L2 all the way to V across Ln. Right? So I need to add them all up. But I know voltage across L1 is L di dt. So it's L1 di dt plus L2 di dt. Remember, i's are the same. All the way to Ln di dt. If I factor out that the Li di dt, whatever resistor I have back there, it is basically the equivalent. Right? So the proof is exactly the same as what we did for the resistors. The second type is just a parallel connection, which means if I have 2 points, 2 terminals, A and B, and having n inductors in parallel, I can replace this by only 1 and the value of the inductor can be computed using this formula. 1 over L1 all the way to 1 over Ln, which again, it's similar to parallel resistors. This is not very difficult. What's very, very, very important is that all these equations that we have for resistors, capacitors, and inductors, they're only true if we only look at, for example, the resistive circuit, a circuit with only capacitors, and a circuit with only inductors. So if I have a circuit that has both, capacitor and inductor, I cannot combine them. I can combine like whatever capacitors I have. I can combine whatever like inductors I have, but I cannot combine the capacitors by the inductors. Right? At least not at the moment. It turns out, instead of looking at the circuit in time domain, which is what we're looking at, if we take the circuit to another domain, which is known as like S domain or Laplace domain, we can treat all these as a resistor, but we have to like adjust the value. We're going to talk about it when we're talking about Laplace transform. But at the moment, if I'm given a circuit, I can only combine inductors, I can only combine capacitors, and I can only combine resistors. If I have a circuit that has all these three, I cannot combine these three. And I have to treat them like completely separately. Right? I cannot combine these three elements to get one equivalent. Right? I can have like equivalent for the resistor, I can have equivalent for the capacitor, I can have equivalent for the inductor, but not the equivalent for the whole thing. Okay? That is very, very important. Okay? So let's do a quick example. Let's just say I am given this circuit. I have a 6 millihenry here, another 6 millihenry here, 6 millihenry here, 6 millihenry here, and then I have 6 millihenry here, and a 6 millihenry. And the question is find L equivalent. what do we have here? Do you agree these three are in parallel? Yes? They have the exact same head and they have the exact same tail. This is the head and this is the tail for all of them. Right? You agree with me? So if I have three inductors in parallel, what is the equivalent? They all got the same value. So it's going to be 1/3 of that. Right? So the equivalent here is 6 in parallel with 6 in parallel with 6, which is 2 millihenry. Right? So what do I have? What do I have? Let me redraw the circuit. Again, let's just call this A, call this B. This is A. I'm going to have a 2 millihenry between A and B. Right? Where does this one go? This should go, let's just call this C. It should go between A and C. This 6 should go between B and C, right? And then I have the 6 millihenry. Right? Do you agree these two are in series? So it's 8 millihenry. How about these two? They're in parallel. So I have 6 millihenry in parallel with 8 millihenry, which is 6 times 8 divided by 6 plus 8. Right? And do you agree this result is in series with the 6 milliamps? 6 millihenry, sorry. So therefore, our equivalent is 6 millihenry plus 48 divided by 14. Right? You with me? Yes. Oh, no. Thank you. Even though they behave as like a resistor, they're inductors. Yeah. Is that clear what we did? Yes? So just like capacitors, this element is also a storage element, right? So we got to be able to find the power and the energy that this element can store. So let's do that. So let's find inductor power and energy. Remember, if I have like the circuit that's connected to an inductor, if current through it is IT, value is L, voltage across it is VT. I know the relationship between V and I is L dit dt. We know this, right? So if we have any element in the circuit, any element, power dissipated by that element equals VI. So power is always equal VI, right? But I know V follows this equation, right? So if I multiply it by I get L IT dit dt. But we know power also is the rate that energy changes over time, right? We know power is dWt dt. So if I want to find Wt, which is my energy, I have to integrate the power. So W of t is integral from minus infinity to t of p tau d tau. Right? Well, what is p? Well, we already computed it as Li di dt. So I have integral from minus infinity to t of Li tau di tau d tau d tau. So this d tau and d tau cancel. What I have here is integral from minus infinity to t of L, which is a constant, I can pull it out, I tau di tau. Right? So again, if I call this I tau apple, I have integral of apple d apple. What is that integral? It's half of apple squared. Right? So this integral is half of L I tau squared. That should be evaluated from minus infinity to t. But I know I at negative infinity is 0. So this is only half L I t squared. Right? Which basically means on average, this is the energy that we have. Right? That's the average of the power that we have. Right? Any question on this? Is that clear? Yes? No? Yes. Yes, that's Wt. So let me quickly write it over here. Wt equals half Li squared t. I can compute it at any given time t. Right? All right, let's do an example. See like how this works. Example. Let's just say I'm given a circuit that's connected to an inductor with value L, and I know L is 10 millihenry, and voltage across it is V of t. Right? We know I of t, which is current through this inductor, follows this graph. So I of t, milliamps, and this is millisecond. It looks like this. This is 2. This is 4. And the value here is 20 million. The question is, given current through the inductor, what is voltage across it? Right? First of all, let's check a few things. We talked about an inductor and current through that inductor being continuous. We talked about it. If you look at the I of t that we're given here, it is indeed continuous. But we said voltage across the inductor might not be continuous. And as a matter of fact, it is not. Because if I look at the voltage across means I have to take derivative of I of t. And since I of t is piecewise linear function, the derivative of I of t means I have to look at the slopes for each portion. For time between 0 to 2, the slope is positive. For times between 2 and 4, the slope is negative. Therefore, what it means is that if I look at voltage for times between 0 to 2, voltage is positive. But for times between 2 and 4, the voltage is negative. So there is a jump that's happening exactly as t equals 2 milliseconds. So voltage might not be continuous. In this case, it is not. But let's just actually like work it out like mathematically. So for times between 0 and 2, I know v of t is L dit dt. But I know this dit dt is the slope. Right? What is the slope over here? Well, remember, just a reminder, if I have 2 points x1, y1, x2, y2, if I want to look at the slope, this slope is y2 minus y1 divided by x2 minus x1, right? Right? We know that. Therefore, this slope here is 20 minus 0 divided by 2 minus 0, which is 10, right? Therefore, this voltage is 10 millihenry times 10, which equals 100 millivolts, right? Right? For times between 2 to 4, and again, I'm being a little sloppy here because I included 2 here and 2 here, but it's just 1 point, it doesn't really matter. Vt is also L di dt, right? Again, this di dt is the slope of this line because it's a piecewise linear function. So again, that's the slope. But in this case, the slope is 4 minus 0 minus 20 divided by 4 minus 2, which is negative 10. As we expected, because it's going down, right? Therefore, Vt is 10 millihenry times negative 10, which is negative 100 millivolts, right? What is voltage for times outside this interval? What is it? It's 0, right? Because I of t is 0. So Vt for otherwise, Vt is 0. So if I plot it, this is what it looks like. This is Vt. Let's just say it's millivolts. This is time, which is millisecond. For times between 0 to 2, the value is 100. The value for times between 2 to 4, it's negative 100. For the rest of them, it is just 0. Right? And as you can see, there is a discontinuity at this point. Which, by the way, means like if I look at the value of voltage a little bit before 2, it's not the same as the value of V a little bit after 2. Right? A little bit before 2, the value of voltage is 100. A little bit after, it's minus 100. Right? So there's a jump there, which is not true about I. Right? If I look at I at 2, the value is exactly 20. Right? if I basically approach t equals to from left and right, they both meet at the same value, right? So what we're going to be doing next lecture, we're going to start analyzing circuits using like these things that we learned. But keep that in mind. All KVLs and KCLs that we learned before, they still hold. The only thing that changes is the relationship between I and V. So if I'm writing a KVL, when I'm writing voltage across, for example, an inductor, I have to write it in terms of like the derivative. When I'm writing like the KCL, for example, for the capacitor, I again have to write it in terms of derivative. So our KVL and KCLs become differential equations. So to be able to solve a circuit that has either capacitor or inductor, or both of them, we're going to end up solving a differential equation. We're going to start by first order circuits, which means our circuit only has a capacitor or an inductor. And then we're going to work our way up to circuits that have like both inductors and capacitors. And we call them like second order circuits. Either way, we're going to have to like solve differential equations, right? We're going to have to like find initial conditions to be able to solve uniquely that differential equation. So what we're going to be doing next lecture, we're going to start analyzing circuits, and we're going to go over like differential equation a little bit. Just make sure we all remember like differential equation. I'll see you guys Friday.